Forward to the clouds.
Okay. For all of our lovely people in the reading group who will probably be watching this on YouTube, we will have today the principles of quantum mechanics presented by Roy, an extremely talented undergraduate in math and physics at LSU, who has been working in quantum research for a couple of years now, I think. So take it away, Roy.
Do you know why it was letting me do it full screen and now it's not?
Technical difficulties.
Yes. I don't understand the
Oh, it was probably because you pressed record. Okay, it's fine. We can I can just use my scroll wheel.
Let me pause.
Actually, that doesn't actually work. The scroll wheel doesn't work. Okay. I'll just press. I'll just press this.
Great.
Okay.
This is fine with me. I'm cool.
Okay, so I just laid out the 4 postulates that both texts actually give the same ones, but the order might be a bit different than what's laid out in the book. So just overview, there are 4 basic tenets of quantum mechanics. So the first is that every quantum system is a vector in a Hilbert space. So that's just like your psi or whatever. It's a vector. You can also, for a closed quantum system, so there's no outside interaction, every evolution of the state is described by unitary operators. I'll go into detail for all of this later. I'm just laying it out to sort of keep it in mind. We also know that a composite quantum system is described by a tensor product of the components of it. So if you had 2 state vectors, you take the tensor product. And then we also know that the measurement of any system will output a certain quantum state with a probability that is the basically the amplitude of the coefficient of that state. So let me move on. So on to postulate 1. So we definitely covered Hilbert spaces before, but I thought I'd just say it again because it's easy to forget this type of thing. So a Hilbert space is just a special type of vector space that has an inner product, and under that inner product, it's a metric space, complete metric space. So I think a complete metric space, that means every Cauchy sequence converges, right? Or
Yes.
Okay. But that's not really that important for what we're doing. It's just good to keep in mind. So we're dealing with finite dimensional Hilbert spaces in particular. So that changes a few things that we just won't get into because it's sort of minor details, but we're dealing with finite dimensional, and since we're looking at qubits in particular, they're going to be of dimension 2 to the n, the Hilbert space. So you have our state vector in the Hilbert space, and you can represent it as a linear combination of basis vectors. So it's normalized, so that means the coefficients squared sum to 1. So basis vectors, that just means it has a magnitude of 1, and every basis vector, the inner product with a different basis vector is going to be 0. And this is just our norm. I don't really like how this came out with like the lines, but hopefully it's clear. The norm, yeah, the norm of a vector is just equal to the square root of the inner product.
Honestly,
So,
the standard notation should just be norm of v with no ket. That would be fine.
Yeah, I did it that way at first, but then I didn't like how I was having to write the inner product. So
yeah.
So now we're getting into qubits specifically. It's really simple. It's just, for a single qubit, it's just 2-dimensional, and you have alpha and beta such that the magnitude of alpha squared plus magnitude of beta squared is equal to 1. So 0 and 1, these are the same as their like classical counterparts. It's just 1. This I don't know if you guys can see my cursor at all.
Yes, we can.
Okay. This first spot is like, oh, we have a 0 value, and this means we have a 1 value. So for 0, it's sort of confusing, I guess, if you're just seeing it. 0 is 1, 0, and then 1 is 0, 1 in the standard basis. So just an aside, for the global phase, we can apply a global phase to any state vector, and physically it will have the same like results. So we can't distinguish between a global phase. And so this is the block sphere. I just pasted out. We definitely covered it a while ago, but I put it again. And then sort of just, I'm not sure if this is like 100% correct, but this is how it makes sense to me, is you know Euler's formula, and it's sort of like a specific spot on this imaginary real axis. So since this is a sphere, there's sort of some redundancy there. So then Postulate 2, we know that for a closed system, evolution is always described by unitary operators. So a reminder, unitary means that the matrix and the Hermitian of the matrix is equal to 1. So what that means in computing terms is that operations on a quantum computer up until measurement are reversible, which is not how most computing is not reversible. So that's sort of part of the reason quantum computing is pretty unique. So I just listed out some common logic gates that are unitary. They have to be unitary, but so the Hadamard will take a 1 or a 0, and it'll put it in like a superposition of 0 and 1. The poly Y gate is essentially a NOT gate, but it's complex, so there's an I there. So that translates to like a rotation on the block sphere. And then we have a C NOT gate, which actually doesn't deal with just 1 qubit, it deals with 2. And it's just, I mean, I've controlled NOT, that's pretty self-explanatory. So this isn't like super important for what we're doing. I just to put some context, here's the Schrodinger equation. We know that the state vector is an eigenvector of the Hermitian, or sorry, the Hamiltonian. Sorry. And then so you usually start with the Hamiltonian, and then you can find like everything else using just general like eigenvector, how you find eigenvectors and things. So I thought there was going to be more people here, so I had some fun exercises, which will hopefully
We'll do it.
Yeah, which hopefully will be really easy. So if someone wants to show this, I don't know if we can.
Should I do it on OneNote?
No, I can write on the screen. Hold on.
There you go.
Pick me, Roy.
Okay. Unless Alex wants to go.
You want to go, Alex?
Take it away.
Okay.
So I just need to show that y dagger is equal to the identity. That's
an upside down dagger.
And that y dagger y is equal to the identity, but
correct.
I mean, oh god, I have a little pin with like a built-in eraser on it, and it doesn't work with this thing. Hold on. All right, is that a better dagger for you?
Yes.
Okay. Y dagger y. Okay, whatever. All right. So 0, 5. Okay. I swear to God, I know how to do matrix multiplication. This is the dagger.
No. No. You did the
My most fun.
transpose, but you
Yeah,
didn't.
you didn't. You didn't take the
Okay.
complex.
Good catch. All right. All right. Yeah, so that will give me that, which is the identity. And then similarly,
We're gonna write exactly the same.
No, it is the same.
it is the same, Zach.
Why it's permission. My dagger is Y. So
I know,
yeah,
but
done.
look, I'm just doing it. I'm checking both. I'm a good student. All right, there we go.
Yay.
All right, let's clear all this off your screen.
All right. So yeah, that was just like a really simple exercise to verify. So if you have something that you think is a quantum operator, you need to make sure it's unitary. Otherwise, you could wreak disaster upon everything. So in this slide, slide 5, I just sort of mentioned the C0 gate, and if you look, it's very different, or it's not very different. It's a different dimension from these two, and that's because you only consider C0 under a composite system. So the third postulate says that you can create a composite system using the tensor product of the two components. So there's another fun exercise, but so just a side note, we call states entangled if you can't factor them out as a tensor product. So that's important, but I guess moving on.
Okay, exercise.
What is the matrix representation of 0, 0?
I mean, you can also write on the screen.
Oh, can I?
Also, just an aside, I didn't mention this. So a lot of times we skip writing the tensor product, like cross sign, and we just write it like this, or we just write it as like 0, 0.
Right. All right, I got this one, Roy. I swear.
Feel free to
Okay.
mess it up like I did.
0, 0. This is the same as 0 tensor 0, which is, I'm going to use the Kronecker product here.
Oh, you mean the tensor product?
The Kronecker product. 0, 0, 0.
Yeah.
Yay!
Yeah, and you can do that for any. You could do that for any of the other states. So that's just a brief, like, this is how it would actually work if you're doing the matrix algebra or whatever. So now we're on to Postulate 4, which earlier I mentioned that under a closed system, every evolution is described by a unitary. Well, when you're measuring, you're actually, I don't know if the proper term is opening the system. That sounds wrong, but it feels right. But it's when the system isn't closed, you have measurement operators, which will essentially give you the probability of a certain measurement, and that but once you apply the measurement operator, you actually change your quantum state. So it's no longer reversible. So this is like the math speak right here. So I guess that would be the probability of a measurement is the expectation value of its measurement operator times its adjoint. So you can see right here, so if it was unitary, then this would just be 1. So then it doesn't really make any sense, which is why we specify this is for non-closed systems. And then after you apply the measurement operator, this is the these sides look different. I'm sorry, but these are both sides. This and this are both sides. So like psi prime after you apply the measurement operator is equal to this expression.
I guess the measurement operator is supposed to be like the operator that projects onto the resulting state.
Yes.
Yeah.
And just a note, so we know that the sum of all the measurement operators in a basis is equal to the identity. So I guess I should probably, can I write? So like, it's sort of, if you had, this is like a really non-general example, but if you had like,
Something
It
about
was-
the dimension here seems slightly off.
what's wrong with the dimension?
What? Oh,
Here, it is. Okay, I'll make you happy.
it's if you're dealing with qubits, then
Yeah.
there's no three-dimensional Hilbert space with
Oh,
qubits.
yeah,
I
yeah.
guess.
Well, I was just, I was
Yeah, no,
just,
it's fine.
it's sort of like, in really rough terms, it'll like return a value out of them. That's not exactly what's going on, but let's see. Right, my mouse is back. All right, here's another fun exercise, which I guess everyone, Alex it's Alex's turn.
Yeah.
Yeah.
Alex.
So
I'm frightened.
remember I was talking about the global phase earlier. So what I said was that you can't distinguish them when you actually measure the system. So basically just prove that. And I sort of, my problem statement was sort of lazy, but just show that psi and then the any global phase applied to psi will be measured as the same.
Where is the? Oh, I see.
So you can go to view options and annotate.
Looks like there is a small typo here. One of them has phi I for the basis. The other one has psi I.
In principle, they could
That's
be different.
correct, but please ignore that. let me fix it. Oh no, 1 second. I need to draw. There, it's fixed.
Good job.
I'm convinced.
All right.
Alex, can you write or? Oh, there's his cursor.
All right.
I'm trying. I don't know if it's gonna come up at all.
There we go. We got a P.
So I'm probably going to do this wrong.
That's okay.
That's fine. Apparently I messed up drawing a dagger and also taking information conjugate. So
We'll only make fun of you relentlessly.
Oh no, this will only be up on YouTube for all posterity.
don't worry, we only have like 4 subscribers. And
It's too
like
many.
2 of them are here.
No! This is gonna take so long.
Are you using your mouse?
I'm using a touchpad.
Oh no.
Does anyone want to take over for me? That's why I didn't want to do it.
You can tap out anyone you choose. This is Roy's show, but
Can I phone a friend? I can't even get past the just rewriting the thing. It's so sad.
I mean, I can do it if you would like. This is disappointing. But yeah, I'll take over. Oh wow. So we got this for. That's not an equal sign. Please
That's a
don't.
colon.
Yeah.
Okay.
And then. Yeah, sorry, these exercises are probably stupid. I thought there would be more people here, so. Why did I write an equal sign?
That's also a colon. I know. This is the most fun talk yet.
So I'm trying to think, what's the most basic way to write this without like skip? Oh, I forgot the state vector.
So don't expand it out. You don't need to.
No.
Okay, so I'm just gonna write this and like skip like one step, but hopefully it's still clear. So that would be.
Yeah, this would have taken me 20
This
minutes.
dagger's a plus sign.
Hey, it's fine. Everything is fine. We all know what I mean. Is that better?
Marguerite said it goes the other way.
Like everybody knows what I mean.
Okay, so these are the two systems, and then these are constants. So you can do e to the minus theta, e to the plus theta, and move them together. For what this problem is, this is taking way too long. So then you add the exponents, and then it's e to the 0, which is 1. So then you just get yay.
Yay!
This is honestly, this is the best one.
Okay, so this backs up what I just randomly said earlier, that you can't distinguish the global phase using a measurement. So let me. How do I?
There's like a clear, like a trash can.
Okay.
And you just throw your writing in the trash can.
All right. So that was about the global phase, but we also have something called the relative phase. So the relative phase, you affect the amplitude, but you do it on a an individual basis, so you can't factor out the e to the I theta. So it's like slightly different. And you can obviously tell them apart using measurement. That's what makes it distinct. So for example, I gave one of the very commonly used bases in quantum computing. This is called the computational basis, right?
0 and 1.
0, 1's computational.
Oh, so this is the plus minus basis?
Correct.
Yeah.
Okay, well, now I feel dumb, but this is the plus minus basis, which you can see the absolute values of the amplitudes are the same, but they are very different, or not very different. They are different because one's a minus and one's a plus. But if you wanted to check, both of these states are still normalized to 1, so they're both valid states. So this is what Zach was mentioning earlier, where we can consider quantum systems under projective measurement specifically. So PM is the projector onto the eigenspace M, which, if I understand correctly, the eigenspace M is the space created by all of the eigenvectors of a value M. So like you use the eigenvectors as a basis, and then you get this space.
Yes, sir.
So then you can sort of simplify what you were doing earlier. So instead of having to do M dagger M, you can just do P of M, or P, which is so just the expectation value of P. And then you know the average value of just any measure, where the measure is this sum, this linear combination of projections. You just do this real quick. So this is related to like the standard deviation. We know the expectation value of M squared. The square root of the expectation value of M squared minus the expectation value of M squared is equal to the variance. And this is actually where the Heisenberg uncertainty principle came from, which I was going to have you all prove, but then it was either going to take forever, which it probably would have been fine because this doesn't take as long as I thought, but it was either going to take forever or I had to give you like literally everything. So I just skipped that and instead I wrote it out for you. Or I guess typed. The Heisenberg uncertainty principle is related to this variance using projective measurement. So if you have you know that A and B are unitary, and then the expectation value of AB is just a generic complex number. So you can find, so then if you apply the commutator and the, I forgot what this is called. This is
Poisson bracket.
the what?
Or no,
That's
not the
the-
Poisson.
that's
That's
the
the anti-commutator. Yeah, that's
The
my bad.
anti-commutator. Well, it's just the commutator except you
The plus
add them
Yeah.
instead of subtracting.
Poisson bracket is mechanics. You should
Which,
not
oh
use
wait,
the
someone had a
bracket.
question. Dr. Brown. I don't know what that was in reference to. Sorry. Oh, the variant. Yeah. So I guess I should just write this out. Sorry, I forgot that some people might not know this.
I mean, I literally guessed Poisson bracket knowing that it wasn't the Poisson bracket.
So it's called the commutator because if I'm not sure if that's why, but it's called the commutator, and if things are commutative, then this equals 0. So that's an easy way to remember it. But this is not the case. This is the anti-commutator, you said?
Yeah, so if it's equal to 0, then the anti-commutator.
Why did I do that? I just wrote AB again.
That is a different thing.
All right. So we're looking at the sum, the sum of these two values, and actually I have time. There's plenty of time. I can just write out the steps for this. So I guess I'll make a new
Gotta
slide.
bust out that MS Paint.
Oh yes. Yeah. Let me. I actually had Microsoft Paint pulled up already because I knew this would happen. So.
Oh my god, it's so small.
Yeah. Sorry. So we have. Okay, this worked. Okay, so we're trying. I have to remember the problem statement. Okay, so we have that these two unitaries. That's awful. I'm sorry. We know that they have an expectation value of some generic complex number. So if we wanted to sum the expectation value of the commutator and the anti-commutator, first let's just find those values real quick. So these are linear operators. So that's just oh, that side actually looked pretty good. So this is equal, we know this is equal to x plus iy, and this is minus x minus iy. So then that equals 2iy. And then we know, I'll skip a step since we already did this.
Or A and B Hermitian.
Are we assuming A and B?
They're unitary.
Unitary.
So we know this is equal to x plus x minus iy, then that equals to 2x. All right, so that's the step I skipped in the PowerPoint, but I'll go back to the PowerPoints, and then let's see. For some reason I have 2 PowerPoints up, but this is the right one. Okay, so then we have that they were equal to, if you take, I guess I also didn't write out this step. Sorry. So it would be 2x squared plus 2iy squared. So be 4x. Or sorry, I skipped something. This is important.
Unless you set I equal to 1.
Yeah, and I also didn't write the I. I tried, but it failed. So then we get that's equal to oops, sorry. Okay, so that's this sum, and then we know that the absolute value of this is squared is equal to x squared plus y squared. So obviously you can see this is equal to 4 that. So then the Cauchy-Schwarz inequality is does everyone knows what that is, right? So the Cauchy-Schwarz inequality, we know that AB, or we know that this is I'm sorry, this is really rough looking. We
get the alligator mouth. It makes sense to me.
Yeah, it's less than or equal to this value, and then wait, that's literally
4
what was written
times
here.
4.
Well, I was excluding the 4, but
Right.
then I realized this was already written, so I don't know why I just didn't say that. But anyways, so we know this is true, and then this is another step I skipped. There's a lot of skip steps here. Let me just write it out. So then, if we know that I really don't feel like writing this up, but I'll do it. Oh, I can just say it out loud. This is easy. Okay, so we know that this sum is true, and we know that this is less than expectation value a squared times the expectation value of b squared. So then we can conclude that since these are both positive, real valued, we can conclude that the expectation value of the commutator squared is less than or equal to 4 times the expectation value of a squared times b squared. So that is the Heisenberg uncertainty principle. But that's not how we normally see it. So I forgot to write this down. Wow. So, but we can get the normal uncertainty principle, which is this is a particular case of it. It's h bar over 2, right?
Yes.
So ow. Sorry, I just like slammed my elbow on the desk.
Yeah, because injuries as well.
So if we substitute a and b with say a unitary minus expectation value, then we will get that the variance, which is what I was talking about earlier, that's why I brought it up earlier, the variance is equal to the expectation value over 2 of the commutator. So I was going to have an exercise where I made you prove this for x and p, but then I realized that it wouldn't make any sense because you all haven't had quantum, and so you wouldn't be able to get all the values, and then I would have had to give them all to you, and then you just literally multiply them together. So I thought that was boring. But that's like that's where this. What did I just do?
You just dragged your slide.
So that's where
Nice.
this famous relation comes from. The uncertainty of x and the uncertainty of momentum are always greater than or equal to the it's the Heisenberg limit. That's the term, right? Okay. Which is just
Go on.
what were you saying, Marguerite?
No, go on.
Oh, I was done. This was the last slide.
Okay, I was gonna note that like technically this is the Heisenberg limit is the h bar over 2, but just be careful because people tend to use that to refer to specific like bounds. For instance, on measurements. It's just like a terminology thing, I think. But you're right. You were right.
Oh, okay.
The key point is that you're right. All right. I have a question.
Yeah.
So in quantum mechanics, there's no time operator. So where does the uncertainty relation delta E, delta T greater than or equal to h bar over 2 come from?
I
vaguely remember something from quantum mechanics, but I don't really recall.
So I don't know, but it's probably related to Marguerite definitely knows, so she can help. But it's probably related to how you, for a constant Hamiltonian, you can generalize it as I think this is correct. So once you get the time independent version, you can create the time dependent version. But I'm sure Marguerite could probably explain the actual reasoning.
Well, I've always gotten the delta E, delta T from manipulating delta X, delta P.
Oh.
I don't remember how to get it directly. I would suspect like you're alluding to, you just incorporate the time product. I know that there is another way to get it.
Maybe it's just like a semi-classical, like manipulating of variables kind of thing. I don't know.
I mean, we can search if you want.
Yeah, that can be something we can all learn together.
Let's look.
Because I definitely should know it.
There we go.
We have to look good for the audience.
You have to share the screen.
Oh, did I not share it? There we go. All right. I guess this is just an example for atomic transitions. So an atom typically exists in an excited state for this amount of time. Oh, wait, this is just a calculation. This isn't the derivation.
But it does look like they derive it from. They start with a difference in
Technical reasons beyond this discussion.
The reason is that the frequency of a state is inversely proportional to time, and the frequency connects with the energy of the state. So to measure the energy with good precision, the state must be observed for many cycles.
So it relates to the frequency phase one. Okay.
Yeah, so I kind of see the intuitive argument, but I would like to have seen the actual math. Okay.
I believe you can derive the uncertainty principle from any canonical relation, I think.
That's the commutation relations. But the issue for this one is that there is no time operator, so you can't do that.
Yeah.
Maybe that'll be like our discussion time for next talk.
Yeah.
We'll begin the talk.
Homework.
Yeah, we'll begin the talk proving to each other the uncertainty relationship for energy and time, and everyone else will be like just lost. And it's great. It's what they'll deserve.
All right. Do we have any other questions for Roy?
Yeah, I can do POVM in another presentation if you'd like. I feel like it would have gone way over time if I had tried to shove that in there.
That's fair.
Do we want to like add it to the spreadsheet?
Let's see. Yeah. Yeah, let's just stop them.
I mean, I kind of